Session 3, here we come. We're still working on Unit 2, the trig functions. We're all set with knowing what the 6 basic trig functions are. We can evaluate trig functions if we know a point on the terminal side of an angle in standard position. If we know the trig function for an angle, we can calculate the other trig functions of that angle. Of course, what was the other thing that we found was helpful? We wanted to know which quadrant we were in, right? That can help us a lot to know just what those other functions are. And we learned I hope it's helpful, way of remembering which functions are positive in which quadrants. We've got all are positive here. Sine and its reciprocal partner, sine and cosecant. Tangent and cotangent. Cosine and secant. So all positive here. So remember this is all St. Thomas cousins going right around counterclockwise. Today we're going to work with both of these. Establishing the domain and range for all 6 of the trig functions. And we're going to be looking at these very famous, or as Stu Schwartz refers to them, special triangles, or sometimes he calls them the friendly triangles. Well, why do we think of them as friendly? Because their relationships, the side length proportions, are fixed and help us to remember the ratios. We'll spend a lot of time with that today. We're going to start by a little review of your quadrant angles. Remember those? We're going to calculate the following. We've got 5 times the sine of 90 degrees minus 12 times the cosine of 180 degrees. Now, as you do this, you want to mentally think of that diagram we used in the last lesson. The sine of 90 degrees would put us right up here. And if we assume that we're using a radius of 1, the sine of 90 degrees will have a denominator of 1, and what will the numerator be? What would this point be right here? It would be 0 for x. Oh, I don't like that. It's trying to translate what I'm writing. 0 for x and 1 for y. So this would be 1 over 1. And cosine at 180, that would be right over here. And what are the x and y if we've got a radius of 1? It's a negative 1. And that's a comma. 0. So the cosine of 180, it's going to be negative 1 over 1, negative 1. So we can simplify that to 5 plus 12, correct? Our answer for this one would be 17. How about this one? We're going to have 6 times the tangent of 180 plus 3 times the cosecant of 270 all over negative 2 times the secant of 0 degrees. All right, so 180 we were just looking at. Tangent, of course, is y over x. So that would be 0 over negative 1. That would be 0. Cosecant, what is its reciprocal partner? Sine, right? So we're dealing with radius divided by y at 270 degrees. So let's put that in. At 270 we've got a 0 for our x and a negative 1 for our y. So cosecant will be 1, the radius, over negative 1. So we'll have a negative 1 here. Now how about the secant? Its reciprocal partner is cosine. And we're talking about 0 degrees. That's the only one I haven't put in here, right? That's 1, 0. So secant is a reciprocal of cosine. Cosine, we know, is x over r. That would have been 1 over 1. The reciprocal of that is 1. So we should be able to simplify this. This is easy enough. 0 minus 3 over minus 2, or a positive 3/2. How about this one? We're going to have 4 times the sine of 90 degrees minus 2 times the cosine of 270 minus 5. And then, after we have all that figured out, we're going to square it. What is the sine of 90 degrees? That's right. Is it coming a little quicker now? What is the cosine of 270 degrees? We've got a 0 here for x and a radius of 1, 0. So we end up with 4 minus 5 squared, I should have put an equals, which will give us a negative 1 squared. Isn't that a nice, elegant answer? All right. Woo! Radians. We know what these represent, right? Pi over 2. If we were going all the way to pi, we'd be here at 180. So half of that puts us at 90 degrees. So we'll have minus 6, and whatever the sine of 90 is, we'll get back to it. Minus 5 times whatever the cotangent is of 90 degrees. And that's all over 3. Oh, this is a little tricky. This notation where they put the square right beside cosine and before the angle measure, please note down here. That's simply the notation that's used. What it's really saying is we're going to take the cosine of theta and square the whole thing. Okay, so that's going to be whatever the cosine of 0 is. Oh, and we'll square that. Then we'll multiply by 3. This one, find that cosine of 0, multiply it by 3, and then square it. So we're getting a little practice here in order of operations. I know it seems so simple, but believe me, we all can get tripped up on that from time to time. So the sine of 90 degrees is 1. the cotangent of 90 degrees. Well, the tangent of 90 degrees is y over x. Let's get 90 degrees. 1 over 0, which would have been undefined. The cotangent is x, 0 over y, so that's okay. That's a 0. Now we have to know what the cosine of 0 is. It's 1 over 1. So here we put it in 2 places. Now we can start to simplify. This will be a 0 we're subtracting, so negative 6 in my numerator. And down here I've got 3 minus, and this one I multiply cosine of 0 times 3 before I square, so I end up with a negative 9. So I've got minus 6 over minus 6. I love it when the answer is 1. Go from a mess like this to a lovely, neat 1. So that's an example of using what we know about the quadrant angles to establish the trig functions and evaluate an expression. Something I want to warn you about, you need to watch the context of what you're talking about when you talk about x. There's an x that we track on the coordinate plane as we trace a point which is going around a circle. We've been doing this now, and we just did it with the quadrantals, where we're looking at when x is 0 and y is 1, and then over here when x is negative 1 and y is 0, all these angles. This is when we are tracing an angle as it goes through its rotations. That's how we define a trig ratio when we say, for example, sine of theta is the y value over the r. Or if I were going to be consistent with talking about x, the cosine of theta equals x divided by r. So x in this context is talking about the rotation around a circle to establish what angle we are at. The x-axis along which we track a changing angle measure. So if we are tracking the angle measure itself here, we are going to see the rotation looking like this. Starts at 0. Gee, I should have 2 pointers, shouldn't I? Starts at 0, goes to 90 degrees, okay? Starts at 0, goes to 90 degrees. From 90 degrees goes to 180. Now you see we're tracking a trig ratio, in this case the sine of x. And as we go from 90 to 180, the ratio is falling back to 0. Then as we go from 180 to 270, the ratio is going negative, because down here y is going to be negative. So, and then back up to 0. So one full rotation when we're looking at where an angle sits within a circle, looks like this. A full rotation when we're looking at the trig function, looks like this. So input to a trig function or defining a trig ratio. They're different. I know it confused me, so I'm assuming that it might have confused some of you. We're going to talk about domain and range. You've been there before in your algebra classes. we've got a function, which we're going to call f. The input to it is theta. And we're going to say this function we're going to talk about is going to be sine theta. Here's what the graph looks like in its very simplest form. The very simplest form of a function is something I call the parent graph. I don't think you're going to see this elsewhere, but this is the way I like to think about it. The domain, what would the domain be here? We're talking about what theta could possibly be. Are there any restrictions on what we can have here for theta? There are no restrictions, so it's all real numbers. Another way you may see this written in other textbooks is like this. That's a symbol for all real numbers. You can use that if you want to in your responses. It's a little quicker than writing all that. And what is the range of sine theta, the parent graph? Well, the range is how far, where it exists vertically. And we can see it goes from -1, +1, and back, and back. So it's between the peaks and valleys, which at least in the parent graph are, for this one we're looking at here, function of f is greater than or equal to -1 and less than or equal to 1. Now we talked about this earlier, how a sine function can never be greater than 1. Well, there is a way we could make it greater than 1. I'll show you that later. We could put a multiplier on it. But the parent graph itself can never be greater than 1. Okay, function f is defined differently here. The input is still the angle measure theta, but now we're talking about cosine. For cosine, the domain, the angle measure, could be all real numbers. And its output, it looks very much like the graph of the sine function. But let's just look at the origin to make our comparison. The sine function at the origin, at angle 0, is equal to 0, whereas cosine at the origin is equal to 1. I want to go back for a moment, just take a look at this. At angle 0, which is right here, the sine function, which is y over r, is equal to 0. So at angle 0, the function, which is measured vertically, is 0. If we were looking at cosine, the cosine at 0 is x over r, or 1, and that would be graphed right here, going to 0 as we go to 90 degrees. That's what we see. It's 1 when the angle is 0, and when we get to 90 degrees, it's 0. Then it goes negative and comes back. So again, it's between the peaks and the valleys, and if we're talking about the parent, for the parent graph, the peaks and the valleys are going to be right there. Function f here is talking about tangent. So our input is the angle, talking about tangent, which is y over x. When we graph this, it looks very different. Every time